Hello. Today we're going to be studying 3.5, Perform Basic Matrix Operations. A matrix is a rectangular arrangement of numbers in rows and columns. The dimensions of a matrix with m rows and n columns are m by n. The numbers in a matrix are called elements. Recall that rows will go from left to right, and your columns will go up and down. For adding and subtracting matrices, please apply the following. Simply add or subtract elements in corresponding positions. You can add or subtract matrices only if they have the same dimensions. For example, for this example, we have a 2 by 2 matrix being added to a 2 by 2 matrix. The result will be A plus E, because they're in the same position, and you'll place the result in the position of your new matrix. Let's try this. Example 1. Perform the indicated operation, if possible. If not possible, state the reason. Looking at example 1, we have a 2 by 3 matrix, 2 rows, 3 columns, being added to a 2 by 3 matrix. To find our result, we'll first add the 6 and the 5 and get 11. Your next step, going from left to right, would be to add -1 plus 0. The result, -1, goes in the same position. Next, you'll have 4 plus 1, which will give me 5. You've now completed the first row of this matrix. The bottom row will be found by doing the same thing. This 1 is in the same position as the 8. 1 plus 8 is 9. 3 plus a -4 is -1. And finally, 4 plus 3 gives us 7. And that's what you do to add matrices. Next, we'll do subtraction. Remember that when you subtracted numbers, when you first learned how, if you had -6 minus -1, you would have had to add the opposite. The same thing applies for matrices. You will add the opposite. But when you do the opposite, you have to do it to every single sign in the second matrix. From here, you'll apply the same rules that we just used for example 1. -6 plus 1 gives us -5. 2 plus 0 gives us 2. And -3 plus -4 gives us -7. Finally, -7 plus -8 gives us -15. You've now subtracted and added matrices. Try numbers 3 and 4 on your own. Press pause while you work. After changing all of the signs in the second matrix, you should have gotten -2.5 and 2.5 for your first row, and 5 and then 6 for your bottom row. For number 4, you'll notice that you have a 2 by 2 matrix being added to a 2 by 3 matrix. This is not possible. Because the dimensions are not the same. Next, let's go to example number 5. Perform the indicated operation. This is called scaling multiplication. If you remember the distributive property, you'll be applying the same method to this operation. You'll multiply -3 times every term that's in the matrix. Negative 3 times 5 gives us negative 15. Negative 3 times 2.8, and you can use your calculator for these, and you'll get negative 8.4. Negative 3 times negative 1 gives us positive 3. Negative 3 times 1.5 gives us negative 4.5. Negative 3 times 7 gives us negative 21. And then negative 3 times negative 3.2 gives us a positive 9.6. For number 6, we have a fraction. Doesn't bother us because it's a half. So you'll look at this 1/2 and you'll distribute it to every single term or element inside of the matrix. So think of a half and you're multiplying it by 8. What's half of 8? 4. Half of negative 20 is negative 10. Half of 0 gives me 0. Half of negative 6, negative 3. Half of 1, 1/2. And 1/2 of 2 gives you 1. Take a moment and complete the bottom row. Look up and check to make sure that your numbers match my numbers. If you got 2, negative 5, and 8, you did it perfectly. Try number 7 on your own. Pause now and unpause when you're finished. If you multiplied correctly, your result is negative 8 and 2.2 for your first row, and 15 and negative 18 for your bottom row. Let's continue to examples 8 and 9. Directions. Use matrices A, B, and C to evaluate the matrix operation. As you would if you were substituting in for any other variable, you'll substitute in now instead of just a number, you'll be substituting in an entire matrix. So instead of A, I will write in 1, negative 2, 4, and negative 3. Plus, instead of B, I will write 3, 5, negative 1, and 0. Remember your order of operations. They still apply. So that means you need to multiply before you add. Using scaling multiplication, which we just did, we will get 2, negative 4, 8, and negative 6 for your first matrix, plus matrix B. Combining the matrices, the elements that are in the same positions, 2 plus 3 gives us 5, negative 4 plus 5 gives us 1, and on the bottom row, 8 plus negative 1 gives me 7, negative 6 plus 0 gives me negative 6. Try to do number 9 on your own. Press pause and then unpause when you have finished. If you've done your work correctly, your result should be negative 15, negative 7 for your top row, and 13, 15 for your bottom row. If you did not get it correct, please pause and go back and check your work. Next, we will solve the matrix equation for x and y. To do that, we first need to simplify the matrices on the left. Distribute 2 to each term. Do your scaling multiplication first. So your first matrix will stay the same, and your second matrix will be 10, negative 2 for your first row, negative 14 and 12 for your bottom row. All of that will be equal to negative 9, 4, negative 13, 1. From here, we will add the matrices that are in the same position, or the elements that are in the same position. So negative 2x plus 10. Not like terms, so I'm just going to write them separately. 6 plus negative 2 gives me 4. The bottom row is negative 13, and negative 8 plus 12 would be 4. It's equal to negative 9, negative 13, 4, and y. Didn't change the second one. From here, you'll match up like terms with their position in the matrices. So if we're solving for x, we care about this position on the left side and this position on the right side. We have the equation 2x, negative 2x, plus 10 is equal to negative 9. Solving for x, we'll subtract 10 on both sides and get negative 2x is equal to negative 19. Dividing both sides by 2, or negative 2, x is equal to negative, or positive, just kidding, making sure you're paying attention, over 2. They also asked me to solve for y. So y is in the bottom right-hand corner of each matrix. So 4 is equal to y, or y is equal to 4. Perfect. Finally, in front of you, you have 2 different sections of information. Our directions are find the total number of yearbooks bought by students and faculty. To do this, instead of creating an Excel worksheet, we'll be the Excel ourselves. We will create matrices for each of the situations, starting first with students buying yearbooks. To organize this, we have 2 different categories. And just to be a little bit more politically correct, we'll use male and female instead of boys and girls and men and women. The first category is freshmen. So I'm going to use an F for the first year students. I'll use an S for sophomores, a J for juniors, and an SR for seniors. This is labeling correctly. From here, if there were 26 freshman males, I'd put that value there. Then 39, we had 29 sophomore males, and 27 for the females, just plugging in these values into their assigned spots. 43, and for senior boys we had 44, and for females we had 68. We're looking for the total, so we'll add this matrix to the same one for faculty. Organize it the same way so that our entries will match up. Note there are 7 women and 4 men. This 4 goes on the left side and the 7 goes on the right side. Once you're done creating your matrix for the faculty, add up all of the values and put them in your final answer. Pause while you work that out. If you've done your work correctly, your resulting matrix should be as follows. For males, 30, 34, 32, and 49. For females, 46, 31, 48, and 80. Let's look on to B now. For part B, if the amount of yearbooks sold increased by 5% each year, write a matrix for the amount of yearbooks that would be sold next year. Let's set up an expression. Increased by 5% each year. So we're going to start off with however many yearbooks were sold the first year, plus the 5%, 0.05 increase. of the next year, of that year.